In this video, I'll talk a bit about what happens if you don't have normally distributed data and try to fit normal distribution using the diagnostic plots. In this course, we'll actually use these plots to assess if the residuals of a model are normally distributed, which means the stuff that's left after fitting a model. And actually the models are quite robust, so if there's some violation of normality, that's usually not a problem, especially because of center limit theorem. We do still want to get an idea of what's going on. We also want to figure out why normality is violated. Maybe we're just fitting the data on the wrong scale, for example. Maybe we should rescale the data first, and it would make more sense to interpret it that way. Or if we have bimodality, for example, in the data, right, like this, where we have lots of negative responses versus positive responses, maybe they're just two different groups, and we haven't figured it out. Right? So that's why we want to look at this and want to see, okay, what's going on. If normally distributed residuals are violated, then non-parametric alternatives can be used, or we can transform the data. This is something I'll talk about later in the course, but there's some things we can do to fix it. So it is still important to look at it and to look at the residuals and if they are normally distributed, even if for the most case some violations will be okay. So here's an example of data that are not normally distributed. We have the empirical distribution here, the histogram, and we fit a normal distribution, the theoretical bell shape here. And let's say we use the mean and the standard deviation we obtained from the data to get as good as possible normal distribution. But we see here that the fit is not great. So what's happening here? There's a skew. So maybe here there's a 0 point, for example, and maybe these are response times, and they can't be below 0. And we get a lot of them here. And then there's like a bit of a long tail like that. That's not normally distributed. Especially the normal distribution would imply there's stuff happening here, even though there's not stuff happening there. And here there's also misfit. Here there's misfit, and here there's misfit as well. So we see it already here. We can look at the cumulative distribution. Oh, this should be cumulative distribution. And we see here as well that here there's a misfit. The theoretical distribution assumes the probability is higher than the empirical distribution does. Why is that the case? Well, that's because of this reason here. Theoretical distribution assumes that there's some probability to get negative responses, for example, or responses below this cutoff score. Well, actually that's not the case. And here we see that here the empirical distribution has a higher probability. That's because we have more data points here above the line. Eventually, of course, it converges to 1. And here you also see some misfit here, that is these points below the line. So what happens if you look at the QQ plot and the PP plot here? Let's first look at the QQ plot. We see that the points are not on the line. Here it's roughly on the line, but here not, and here not. Right, so this would really show us, okay, this is something we don't expect, and this really does not look normal at all. What do we see here? Well, here the points are above the line. And so we have here on the x-axis theoretical quantiles, on the y-axis the sample quantiles, or you can just say sample values. We tend to call them quantiles. So this means that there are data points here that are higher than we expect according to the theoretical quantiles. Why is it the case? Again, because of this cutoff. The theoretical distribution assumes there will be some values below 0 or below this lower point, which is not the case. So these are actually should have been a bit more to the left according to the theoretical distribution, or they should have been lower. That's why the sample values are higher here. Right, so here we see that there seems to be some sort of lower bound, because the sample values at some point stop going down, or I would have expected them to go down. What do we see here? Again, sample values being higher than we expect according to the theoretical distribution. And that's actually these points over here. We see there's quite a lot of data here on the right. That's typical in a right-skewed distribution. Basically, there will be more data still here. Maybe there's some data points here as well, which are these outliers that are higher than what we expect. We don't really expect anything beyond this point here in this red curve be 0. As we see here and here, clear violations of the normal distribution. Do we see that also in the PP plot? Yes, a little bit different. So here we have the PP plot. And we see here something else. What this shows is this is actually pretty much the same plot as this one, except that you can imagine the red line being stretched out. Right, so we see here the implied probabilities are below what we expect according to the theoretical distribution. Here it's above what we expect, here a bit below, and then in the end it's 1 again. Why are the sample probabilities below what we expect? Because there's nothing below this point here, where we should have expected some probability according to the theoretical distribution. Why is it above here? That's because we have way too many points here. Like at this point here, let's say we draw a line here, and we add all these bars together, that's a higher area than this part of the curve in theoretical distribution. The more observations occurred left at this point than we expected. And that's why we have this area above the curve. And so we see that both plots show us violations of normality. They both show us something different. The QQ plot is really about these differences, and it will show outliers really well. Where the PP plot is really about these differences here, especially this one, but you can also imagine it here, where it shows that the probability is actually matching what we expect. Here we have another plot, where again we see that the normal distribution is not matching, because we have two modes. Now in this case, it's actually pretty hard to see this in the QQ plot and PP plot, but the histogram is pretty clear, right? So here, maybe these are two different distributions, maybe we miss a group. So maybe we measure height here in meters, right? And maybe we did not take into account that we have men and women in the sample, right? So maybe this is the peak for women, this is the peak for men, and there's some difference in them. And if you would actually look in the group, we would not have a difference. And that's actually a reason why we look at the residuals and not at the data itself. Let's say we want to measure height, and we have two groups, so our dependent variable is height, or outcome variable is height. Our independent variable predictor is gender, and we want to predict height from gender. You would probably get a significant effect, but probably the height itself should be bimodal, because we have two different groups, but we're taking that into account in the model. That is why we look at the residuals instead. All right, do we show this in the, see this in the, this should be a cumulative plot here. Do we see this in the cumulative plot? Yes. You see here, there's a peak where the probability is higher, that's here. Then here it's lower, that's this part here. And here again it's higher, it's a bit of this peak here. But it's hard to see, it's easier to see in the histogram. So what do we see in the QQ plot? Mainly what we see actually is not really the bimodality. It is more that these points are not wide enough. We see that this between these lines here, we have pretty much all the points, where the normal distribution expects some more points to be a bit further away. That's why we see that in the sample quantiles, these are too high. And at the end, these are too low. We would expect some points to be further off, which is what we see here in the QQ plot. In the middle, it actually looks okay. So basically, here, this value here, if we draw a line here, then indeed half the points are below this, half the points are above it. So that quantile is actually the same. So we don't really see the bimodality here in this plot, but we see that here the distribution is not fitting. In the PP plot, we actually see the bimodality a bit more. As you see here, it's too high here. It's this plot here. Then for a while it's too low before it gets too high again. We don't really see here that the histogram is too narrow, but we see that the shape is not correct, which is what we see in the PP plot here. And let's look at the final example. Here we have outliers. So the data here is actually really normally distributed. Or this is a bell shape, except that I simulate a few points here that are just very far away from this bell shape. These are clear outliers. And Do we see that in the plots? Well, yes. First of all, the theoretical distribution is made too wide. So we see, for example, here in the cumulative distribution that it expects more cases to be left of where it's actually samples and more cases to be right where it actually samples. So that's an interesting thing. We see this in the PP plot, right? This is the same shape really. We see that, again, it's too narrow. So here, for example, we see that this is a bit flat. There's actually something we see here as well being flat and here as well, but a little bit too narrow. We don't really see the outliers in the PP plot. We see them here in this QQ plot. Because this is about, PP plot is about this height. It's actually not that different, there's very tiny peaks here. But QQ plot is about these distances here. And that shows very clearly that these are way too high. They're much higher than what we expect according to this distribution, right? These outliers here. Which is very clear to see here in the QQ plot, especially. Right, so outliers might actually have a very severe impact on the results. And you want to find them. But the important thing is not to just remove them, right? Because you don't want to remove data just like that. Like data is valuable. Any data that you have is valuable. You want to check if these outliers are actually, what's the reason for them? What are they? Who are they? Why are they outliers? So maybe they're just data entry errors, or maybe the subject's not responding seriously. Then you might want to remove these. But maybe there's a genuine reason why these are outliers, and we should have them in the data. And we should actually explain them, why they're happening. If you do want to remove them, some strategy we can do. Well, you can try to identify them, remove them manually, but it's a bit arbitrary. A more structured strategy would be to trim the data, where you remove, for example, the top and bottom 5% of the data. This by default remove the highest 5% of your data points to make it a bit more narrow. Winsorizing the data. This is a bit weird, but basically what you're doing is you're not removing the data below the bottom 5%, the top 5%, but rather you're replacing them with the 5th and 95% percentiles. Let's say we have data on a range. And let's say we have all these data points here, lots in the middle, few here, few more, like that, for example. And let's say for this point here, we have that this is 5%, 5% data. In that case, what we could do, in trimming, we just remove these. In winsorizing, we would basically place them here. Place them back. Remove them to this border, from which we would have removed them otherwise. Older research actually tends to use z-scores, so we calculate the z-scores and then remove data based on z is above 3 or z is lower than -3 or maybe 4 or 5, which is something you can do because you don't expect z-scores to be above 3 or below -3. But this is not really recommended anymore. And for that, I'll refer to the field book and the readings that are listed on Canvas. So ideally, and this is really important, you determine which threads you're going to use to handle the outliers before you collect the data. The reason is that you don't want to be able to cherry pick. If you do, and you might choose whatever outlier removal strategy works best to get your significant effect. If we do that, we might get a higher chance of getting a significant effect, even though the null hypothesis is actually true. We no longer have our alpha rate fixed at 0.05. That is hugely problematic, because we might think that our effect is significant, even though actually it's not. We were just trying as many things as we could until we got a significant effect. That's not something we want to do. And so ideally, you want to say, okay, we're going to trim the data or wincherize the data, or maybe even use z-scores to handle it, or something else, before you collect your data. Right, it's also important for example, in this course, if you do a project, you want to have an idea about, okay, what am I going to do to outliers before you even start collecting the data, because otherwise you already have your data and you might already see, okay, if I remove this outlier, I get a significant effect. If I move that outlier, I don't. And that's, yeah, actually then bordering on fraudulent research. Right? So that's not what we want to do. Okay, that's it for this video series on normality and fitting distributions and outliers.